I'm Mercarenes, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Today's challenge is problem number 22. We're given a list of 5,163 names. Our task consists of two parts. First, begin by sorting the list in alphabetical order. Next, calculate the alphabetical value of each name and multiply it by its position in the list. The problem description shows us the name Colin as an example. Colin is a 5-letter word, and to calculate its alphabetical value, we sum the numerical values of each letter. C is the third letter of the alphabet, so it gets a value of 3. O is the 15th letter of the alphabet, so we write a 15 for it. L is the 12th, I the 9th, and N the 14th, for a total of 53. After alphabetizing, the problem tells us that Colin will end up at position 938 in the resulting list. So we multiply 53 times 938 for a total value of 49,714. Let's see another example. The first name in the list before sorting in alphabetical order is Mary. M is the 13th letter of the alphabet, A is the 1st, R is the 18th, and Y is the 25th, for a total of 57. We don't yet know where this value will end up in the sorted list, so we can't calculate our final value. Today, we'll be starting our draft in Scala. Scala is a language that runs on the Java Virtual Machine, or JVM, and it was one of the earlier languages to reach some level of recognition by marketing itself as a Java alternative. Scala later inspired many of the features that went into Kotlin and Salon, as well as the functional .NET language F#. Scala markets itself as a functional object-oriented programming language, capable of supporting code written in extremely functional or object-oriented styles, depending on what the problem requires as well as the programmer's own preference. We'll start by writing a more imperative solution to this problem, and then we'll talk about how we can make it more functional. First, we'll write a function to calculate the alphabetical value of a name. I'm writing this in Scala 3, which came out in 2021. One of the myriad of new features available in Scala 3 is the ability to define functions at the top level, as opposed to within a class like Java and the JVM normally expect. If you're following along at home in Scala 2, you'll need to wrap this function in a singleton or package object. Regardless, the implementation is fairly simple. We start our score at 0, iterate over each character, and add the character's numerical value to the score, where the numerical value of a character is its distance from capital A in ASCII, plus 1 to make our values start at 1 rather than 0. Finally, we return the score. Like Ruby and many of the languages we've worked with in this series, Scala will happily return the value of the final expression in a function, even if you don't explicitly preface it with the return keyword. Before we move on and write the rest of this code, there's already one thing I want to draw your attention to. It's a subtle point, but it's one that will come up a few times today. Scala is a JVM language, which means it uses the same basic types as its host, the Java Virtual Machine. Our name argument is of type string. This isn't a Scala wrapper for strings. This is actually Java lang string. That is, it's the same type Java uses for strings. But if you're familiar with Java, that raises a question. Java strings are not iterable. If this was Java, we would have to either convert the string to an array with tochar array, or iterate over the indices using an old-style for loop. So what is Scala doing here to make this work? In fact, Scala doesn't use the iterable interface in for loops at all, at least not directly. The desugaring algorithm of Scala for loops is a bit complex, but in this case, we'll end up delegating to the for each method on the type. So our for loop is actually equivalent to this form. For each doesn't come from an interface like iterable. Scala admits a form of duck typing here. Any type with a function called for each that accepts a function as an argument is admissible in this form of for loop. To be fair though, that raises an even more pertinent question. Not only is string not iterable, but it also doesn't define a method called for each. This is another place where Scala steps in. For each is defined using the extension method pattern on a Scala class called stringops. Stringops is a built-in Scala class with a single private field of type string, which acts as a decorator for the string class. And the syntax of Scala is kind enough to let us call methods on that class without ever explicitly constructing it. So in reality, our nice short for loop is equivalent to this. Except that since stringops is declared as a value class, the allocation of that intermediate object is guaranteed to be optimized away by the Scala compiler. Regardless, we have a much prettier for loop and don't have to think about all of this type resolution. And with that, we've got our alphabetical value function. Now let's write our main function. Again, the syntax for this changed between Scala versions 2 and 3. So if you're on Scala 2, you'll need to write a Java-style main function with a string array as argument. In Scala 3, we can simply mark a zero-argument function with the main annotation. We start by reading the whole file in UTF-8 using the source object, which gives us a buffered reader. We convert that buffered source object into a string and then get rid of the new line at the very end. Scala provides two ways to declare local variables, and we've used both of them now. If the variable's value is going to change, we use the var keyword, as we did in our alphabetical value function. If the variable's value is not going to be reassigned, we use the val keyword, short for value. You can think of the val keyword as being similar to Java's final keyword. Note that val, like final, only guarantees shallow immutability. That means that while we can't reassign the variable itself, we can mutate the thing inside the variable just fine. Now, our input file consists of one line, with commas separating the names and quotation marks surrounding them. We currently have a string containing this whole line, and we want an array of strings without the quotes in the names. Split the string on commas, producing an array. Then iterate over the indices of the array, removing quotes in each string. Next, sort the array. Like Java, Scala provides a built-in to do this, so we don't have to write our own sorting algorithm. Finally, iterate over the items, keeping track of the indices as we calculate the value of each word. Print out the final result when done. The zipWithIndex method, as the name implies, pairs each element with its numerical position in the array, sort of like enumerate in Python. This is all we really have to do, but as it's written right now, this is more like Java code than Scala. This is the way an experienced Java programmer might approach this problem if they were just introduced to the Scala programming language. Before we change anything semantically, I'd also like to add that Scala 3 introduced a new quiet syntax which removes a lot of the parentheses and curly braces in favor of indentation sensitivity. This new syntax is 100% optional, and the classical approach still works. But if we're so inclined, we can use indentation to signal the start and end of our functions and loops, rather than braces. The Scala community is fairly split on whether or not this new syntax is to be preferred, and I suspect that won't change for a while, but since it's a shiny new toy, I'll use it today at least. Now let's talk about how to make this a little more functional. We'll start with the alphabetical value function. I already mentioned that through the stringops class, Scala gives us the for-each method on strings, despite it not existing in Java. But that's not remotely all that stringops gives us. This extension class provides us with a whole collection of Ruby-style enumerable methods. So rather than our 4-line imperative function before, we can write this very neatly with a couple of higher-order functional calls. In English, this reads as, take the name, convert each character to its numerical value, then sum the result, which is how I would like to think of this problem algorithmically in my head. Let's see if we can iterate on our main function similarly. First, our for loop, which removes the quotation marks, is pretty clearly a map operation. We're applying some particular operation, in this case removing the quotation marks, to each element of the list and storing the result in a new list. So we can convert that to a call to the map function. Similar to strings, arrays in Scala are simply Java arrays. So this map function is provided by the arrayops class, which is an extension class just like stringops. Next, we can call the sorted method on our array, again through the arrayops extension class, to produce a sorted array functionally rather than mutating the original. Our last for loop is another summing loop. So we take our names array, zip it with its indices, turn each name into its numerical value, and then sum the result. We've turned a 26-line imperative solution into a 12-line functional one. We've removed all traces of explicit mutable state from our code and made the flow match our intentions quite nicely. This is basically what our final solution is going to look like today, and we'll be working in a functional language. But first, a brief history lesson. The year is 1986. The telecommunications industry is booming. The old manual switchboards are going the way of the dinosaur, and whoever can scale up their communication systems the best is the winner. A Swedish company, Ericsson, seeks to get the edge on their competition with the development of a new tool called Erlang. The initial implementation of Erlang was written in Prolog. Yes, you heard that right. The initial implementation of Erlang was written in the logic language Prolog. The prototype was a success and proved to be able to handle the industry's unique requirements well, but Prolog's slow and unpredictable performance made the tool a non-starter for use in real systems. Fast forward to 1992. Bogdan Hausman developed the Beam virtual machine, which compiled Erlang code into bytecode, which was then interpreted using a virtual machine written in C that has a focus not just on speed, but on high levels of concurrency. The Beam is a success, with Erlang as its flagship language. But there's one small problem with that prevents widespread adoption. Remember how I said that the first Erlang interpreter was written in Prolog? The folks who developed Erlang really liked Prolog, and it shows in the language's syntax. For example, this is a quicksort algorithm written in Prolog, and this is the same algorithm written in Erlang. The exact specifics here aren't important, as the point I'm trying to draw is how similar the syntax is. 2 decades later, in the year 2012, Jose Valim introduced the Elixir programming language. Elixir is the second major language to run on the Beam virtual machine and maintains full compatibility with existing Erlang tooling and libraries, all the while applying a fresh coat of paint to the syntax and making the language look more like Ruby than Prolog. In some sense, you might say that Scala is to the Java virtual machine what Elixir is to the Beam virtual machine. Elixir is the language we'll be using today. Elixir is a high-level functional programming language, and due to its presence on the Beam platform, it places a heavy emphasis on concurrency. An Elixir program is organized into modules, which contain functions. Modules begin with the def module keyword and end with the end keyword. Likewise, functions begin with the def keyword and end with the end keyword. If you're just writing a few toy lines of code, you can write them at the top level. But if you're doing anything more sophisticated or defining functions, you'll need to write a module. Here's a basic hello world function in Elixir. At its most basic, Elixir looks a lot like Ruby. And like Ruby, parentheses on function calls are generally optional unless required for disambiguation, which is why our hello call doesn't have parentheses at all, and our io.puts call simply has its argument written next to the function name. The basic data types in Elixir are more or less the same as in Ruby. You've got integers, floats, and strings, as you might expect. Booleans and the special value nil are written in all lowercase, whereas Erlang follows the prolog convention of treating lowercase names as atoms and uppercase names as variables. Elixir precedes atoms with a colon and writes variables in lowercase. An uppercase name in Elixir is also an atom, but it undergoes name resolution. So, for instance, the uppercase name string statically expands to the module name elixir.string. Some programming languages support so-called function overloading, where multiple functions with the same name can be defined, provided they can be distinguished by their argument types. We saw this most prominently in Julia, which supported full multi-method dispatch. On the opposite end, many dynamically typed languages forbid function overloading and only allow one function with a given name and a given scope. Elixir takes a hybrid approach, and it's the same approach that Erlang took before it and Prolog before that. In Elixir, functions can be overloaded by their arity, but not by their types. So you can have multiple functions called hello, provided they take different argument counts. To refer to a function as a first-class value unambiguously, we write it like so. First, an ampersand indicates that we're talking about a function. Then we specify the name, followed by a slash and the expected number of arguments. Elixir provides two basic ordered collection types, lists and tuples. Lists are always singly linked lists and are written using square brackets, while tuples store their data contiguously and are written using curly braces. Now, Elixir takes its status as a functional programming language very seriously, so all data types in the Elixir programming language are immutable. This means that once we've constructed a linked list or a tuple, we can't change its elements, but can merely construct a new lookalike. On the other hand, Elixir is dynamically typed, so both lists and tuples can be heterogeneous. That is, the data they contain is not restricted to just one data type at a time. Maps, which associate keys to values, are written preceded by a percent brace and terminated by a closing curly brace. Maps support any Elixir value as the key, including lists or other maps. Branching works about how you'd expect. The if keyword takes a condition and a block to execute if the condition is true. It also supports an optional else block. The unless keyword inverts the condition but otherwise works the same. Elixir follows the Ruby rule of truthiness. The special constants nil and false are considered falsy, and all other values are considered truthy. We also have cond, similar to many Lisp dialects, for checking multiple conditions in order. This is a cleaner alternative to a series of if-else clauses in a sequence. And finally, we have case for pattern matching, which we'll see an example of soon. Since data in Elixir is immutable, there's not much sense in a while loop, as such a loop requires the condition to change at some point in order to be useful. Many looping constructs can be done with a collection of built-in functions that provide a stream-like API, such as enum.map and enum.filter. And for use cases not supported by the standard library, we simply employ recursion directly. Let's write some Elixir code to sum the first few even squares. That is, we'll take the first 5 even perfect squares and sum them. Ranges in Elixir are written similarly to Ruby, so the range of numbers from 1 to 10 is written with a double dot in between. Elixir isn't an object-oriented programming language, so values don't really have methods. The basic streaming API is defined on the enum module, so to keep only the even values, we call enum.filter with an appropriate lambda. Then we call enum.map to square each value and enum.sum to sum the result. Finally, we print it out. This example is important because it illustrates a common problem with languages that provide functional primitives in this way. Humans, at least those of us in the English-speaking world, generally read left to right. Intuitively, this line of code should read, take the range from 1 to 10, filter it, then square each element and finally sum the result. That's how I think of this function in my head. But if we try to read it left to right, we get, sum the result of mapping the result of filtering the range from 1 to 10 by taking only the even values, squaring each element. Not only is the code not reading left to right, but it's almost inside out. The starting point, or the first thing to happen, is right in the middle. Fortunately, Elixir has done some work to remedy this. In Elixir, we can use a vertical bar followed by a greater than sign as a pipe operator, which passes its left-hand side as the first argument to its right-hand side. So we can rewrite our expression like so. From left to right, this reads, take the range from 1 to 10, filter to keep only the even values, square each value, and then sum the result. That's the order I want to think about this expression in. Since I briefly touched on quicksort in Erlang and Prolog, let's write a quicksort algorithm in Elixir. Quicksort is a common algorithm for sorting lists taught in undergraduate computer science courses. It works by taking the first element of the list, which we call the pivot. Then we look through the rest of the list and partition it into 2 pieces, based on which elements are less than the pivot and which are greater. Recursively run the quicksort algorithm on the 2 parts, so that we have 2 sorted lists, then insert the pivot in the middle, since we know it's bigger than every element of the first list and smaller than every element of the second. On average, this will iterate over the list in log n time. Let's see an example by hand. Suppose we want to sort the list 4, 2, 7, 1, 3, 6, 5. Our first element is 4, so we'll take that as our pivot. We go through the rest of the list and split it into 2 parts. Those that are less than 4 and those that are greater. Our less than list is 2, 1, 3, and our greater than list is 7, 6, 5. Now we recursively run quicksort on each of those. For our lower list 2, 1, 3, we get a pivot of 2. Our lower list in this recursive case is 1, and our upper list is 3. Both of these technically get their own recursive step, but there's not much to do with only a pivot and no tail list, so we just get the same lists back. We group those together with our pivot and get 1, 2, 3 as our lower list. Our upper list is 7, 6, 5. The pivot is 7, so we split on that. In this case, there are no upper values, so our upper list is empty and our lower list is 6, 5. Recursively, the lower list's pivot is 6, so 5, which is less than 6, goes into the lower list, and our sorted list is 5, 6. The empty list doesn't go through a recursive step, so we put it together and get 5, 6, 7. Finally, at the top level, we append all of our lists together with the original pivot of 4 in the middle and get a nicely sorted list. Great, let's do it in Elixir. First, we define our base case. If we try to sort the empty list, we simply get the empty list. Easy enough. Next, we'll define our recursive case. Elixir functions can have multiple clauses, and those clauses can pattern match on their arguments. So since we know the list isn't empty at this point, we'll destructure it into its head and its tail. This is the same thing we were able to do in Prolog, just using a slightly more Ruby-like syntax. Once we have our pivot, which we're calling x, we construct our lower and upper lists by applying enum.filter to the input, and then quick sorting the result. Finally, we concatenate those together with our pivot in the middle. We can test this by calling io.inspect on the output. io.inspect is your general-purpose debug printing tool, and it's capable of printing any Elixir data structure. The enum module is simply a module full of helper functions. You'll never implement your own version of this module for new types. Most functions in this module end up invoking lower-level primitives in the enumerable protocol, which is where Elixir actually does the dynamic dispatch. You can think of protocols as being sort of like type classes in Haskell or traits in Rust. They allow for polymorphism and are implemented on a type, but they don't couple as tightly to that type as, say, a Java interface. And enumerable is Elixir's version of Java's iterable, though written in such a way as to not depend on mutable state. It's worth noting that Elixir provides a list comprehension syntax that works a lot like for loops in Scala. Specifically, Elixir list comprehensions invoke the same primitives from the enumerable protocol as the enum function, so we could rewrite our filter operations like this. Finally, everything we've talked about so far is eagerly evaluated. In Scala, all of the map and flat map operations are eager. They'll immediately iterate the input list or sequence and produce a new sequence, usually of the same type. For loops in Scala generally desugar to map and flat map as well, which has the effect of making these constructs eager too. Likewise, Ruby's enumerable module will generally try to return an array eagerly unless you ask it not to, and Elixir's enum module works the same way, producing a linked list immediately by default. In each of these cases, we can actually make the result more lazy if we want to. In Scala, we can call view before performing our operations to get a lazy view of the result. In Ruby, we call lazy on any enumerable to get an enumerator that refuses to evaluate its original list until forced to do so. In Elixir, we can use the stream module. The stream module provides basically the same functions as enum, and it's backed by the same enumerable protocol, but it's lazy. So if we were to define our own custom sequence type in Elixir, we would simply have to implement enumerable once, and we'd get access to the lazy and eager modules for free. Now you may be wondering how we deal with data types in Elixir. I already claimed that the language isn't object-oriented, so we won't be writing classes in the usual sense. We have seen a heterogeneous key-value store called maps, which are written in curly braces preceded by a percent sign. Every module in Elixir can define a struct with the def struct keyword. A struct takes on the name of its enclosing module, and the def struct keyword defines the fields available on the struct. Let's define a struct that represents a three-dimensional vector. First, we need a vector module. Inside that module, we define its struct to contain three fields, x, y, and z. Now, to construct a vector, we use the same syntax that we would use for a three-element map, but between the percent sign and the open brace, we put the name of the struct. Elixir will guarantee at compile time that the fields we declared in our struct instance and the fields defined in the def struct match up. Other than that, structs look a lot like maps. Structs don't have instance methods, so we simply define the operations that apply to our struct as standalone functions. By convention, we place these functions in the same module as the def struct declaration. But this is not a requirement, and it does not afford us any special syntax or treatment. For instance, we could define a dot product or inner product function like so. To call it, we simply invoke the function like any other. If you're coming from Ruby or another object-oriented programming language, the lack of a designated self parameter or of special dot notation call syntax, it can be jarring at first, but you get the hang of it surprisingly quickly. Elixir also has very solid support for writing macros. A macro is sort of like a function, except that it gets evaluated at compile time rather than at runtime, and it expands to other syntax in the host language itself. This allows us to write control flow constructs that behave like built-in loops or conditionals. When people think of the word macro, they often think either of Lisp dialects or of primitive text replacement using a tool like the C preprocessor. Elixir macros are a lot more like the former. In addition to if statements, Elixir provides unless statements, which only execute their body if the condition is false. Unless blocks can take an else block, which gets evaluated if the original condition was true. Let's pretend Elixir didn't provide an unless macro and write it ourselves. We declare macros with the def macro keyword. Our macro takes one required positional argument and then two keyword arguments. Macros take syntax and produce syntax, so the result of this macro should be a syntactic form. In reality, this is just a tuple of lists of tuples of lists nested several times deep in a particular format. But fortunately, we don't have to care what that format is, because we can quote Elixir syntax. The quote special form in Elixir works like it does in most Lisp dialects. It returns its argument, unevaluated, as a syntax object. So what we're saying here is this. When a call to the unless macro is compiled, return a call to the if macro, with the condition being our argument condition, and the true and false cases swapped. Unquote is the inverse of quote. If we had just written the word condition here without unquoting, then it would have been treated literally as the variable name condition, which isn't a variable that exists in the current module scope. By unquoting it, we get the value of the local variable condition as a syntactic form. The same is true of our true case and false case arguments. We can call this explicitly, passing arguments for do and else. But we've named these keywords in very particular ways. Macro keyword arguments called do and else have special behavior in Elixir, in that they can be passed as blocks when calling the macro. So we can actually call this macro just like the built-in unless statement. Note that macros are a bit special in Elixir. To use macros from a module, we have to explicitly inform Elixir about our intentions using the require keyword. Currently, our unless macro requires its else clause, but we can make it optional by providing a second clause to the def macro declaration. Now, if we don't pass the else part, we won't include an else part in our generated code either. This is all we need to solve Project Euler today, but we haven't even gotten into Elixir's biggest selling point, concurrency. The Beam platform was built from the ground up with concurrency in mind, and Elixir leverages this to its fullest. Elixir follows the actor model, which means that it views actors who can send and receive messages as the basic building block of concurrent software. The actor, our basic building block, is called a process in Elixir. But it's not an operating system process. In fact, it's barely even a thread. When we think of multi-threaded programming, and especially of multiprocessing, we generally think of processes as being heavy and expensive and having a certain amount of overhead. But that's not the case in Elixir. Processes in Elixir are cheap to create and, in principle, can occupy mere kilobytes of memory compared to the high cost of operating system processes. Elixir gives us a single process to run our application when we start, and we can get its process identifier or PID with the self function. Note that self is not a special keyword. This isn't an object-oriented self. This is just another function in Elixir that happens to be named self. To spin up a new process, we can use the spawn function, which takes a function argument and runs it to completion in a new process. The spawn function returns the PID of the new process. So far, this looks like a pretty typical multi-threading implementation, but every Elixir process gets a process mailbox, and it's through this mailbox that different processes communicate in a complex application. You can send a message to a process's mailbox with send, which takes two arguments, the destination PID and the message itself. The message can be any Elixir object, such as a string, a tuple, a list, or a number. It's very common to send messages as tuples, where the first element of the tuple is an atom indicating the type of message. A process is not obligated to immediately take action on the message. If the process isn't actively listening for messages right now, the message just goes into the mailbox. To receive a message, we call the receive macro, which takes one or more pattern matching clauses. When we perform the receive call, the current process checks its own mailbox for a message and tries to pattern match it against the clauses in the receive block in order. If a pattern matches, the pattern's corresponding body runs. Once the receive block has successfully matched one message, it considers its job done and moves on. If no message matches any of the clauses, we wait until one arrives, which does. The receive block can also take an optional after clause. If an after clause is specified, then Elixir will stop waiting for a message after that number of milliseconds has elapsed, and will run the after block instead. The after clause can also have a timeout of 0 milliseconds, which will cause receive to only check the mailbox for currently existing messages, or to return immediately, not to hang waiting for more. Let's write a basic ping pong server in Elixir. That is, let's write a process which, when it receives a message tagged with ping, responds with a message tagged pong. We'll put our ping server in a module called, appropriately enough, ping. The ping module defines a spawn function which starts up the process and returns its PID. We'll need this PID in order to send messages to it in a moment. The process itself will run the run function, which is declared with def p to make it private within the module. The run function receives a message which is a two-tuple of the form ping, message, and prints out the message. Then we call run again to continue the loop. Remember that Elixir has no while loops, so if we want to run this server indefinitely, we'll just recursively call our own function after each message we process. The Beam platform's support for tail call optimization ensures this won't blow up our call stack. To talk to this basic server, we first spin up an instance with spawn ping, saving the PID to a local variable. Then we send an appropriately formatted message. But I said I wanted the server to respond with a message, not print one out to standard output, so we really should be sending a message back to the caller. But that raises an interesting question. How do we find out who the caller is? The answer actually is that we can't. When an Elixir process leaves a message in the mailbox, it does so with no return address. The only thing in the mailbox is the message itself, so there's no way to identify who left that message. If the sender is intending to receive a response, they need to voluntarily put a return address in the message somewhere. So instead of sending a 2-tuple of the form ping, message, we're going to send a 3-tuple ping, message, sender PID. Inside of our run function, we expect a 3-tuple now, and we send a response to our caller using the PID they gave us. Outside the run function, we send our message, then we expect a response of the specified format and print out when it's happened. We now have two processes that are communicating over a message channel. You may be wondering where all the locking primitives are. We're sharing data across multiple processes that are, at least potentially, running concurrently, so we should lock access to them behind a mutex or a monitor or something, right? Actually, wrong. Every data type in Elixir is immutable. Multiple processes can't concurrently mutate the data in a message because nobody can mutate the data at all. And this is only the most primitive form of concurrency available to us. These actors and their mailboxes are just the building blocks. Elixir provides a bunch of higher level design patterns we can use which leverage the actor model. We can use spawn link to tie two processes together, so that if the child fails, then it takes the parent down with it. The task module spawns actors whose sole purpose is to perform individual short-lived actions and then terminate, as opposed to long-running server processes. GenServer automates the process of building server processes that respond to specific types of messages, either synchronously or asynchronously. Long-lived processes can be chained together in supervisory trees, where the supervising processes know what to do when their children fail. This is how you program in the large in Elixir. Not with classes, but with processes. Your mutable state is encapsulated in standalone processes, and the only way to query a process's state is by asking for it by sending a message. Let's see a concrete example of this. In reality, we'd probably use a GenServer to automate some of the boilerplate, but we'll do it by hand for educational purposes right now. Let's write a process that acts as a mutable map from keys to values. It will accept two message types, a put message and a get message. The put message adds the given key and value to the map, while the get message responds to its caller with the current value corresponding to the key in the map. Our basic setup is the same as before. We provide a zero-argument spawn function that starts up our process and calls the private run function. Note that our run function now takes an argument, which is the current map. When we recursively invoke this function, we might change this argument, which is how our server remembers its current state. Inside the run function, we accept our two message types, get and put. In the case of get, we get the value from the map and send it back to the caller. In the case of put, we don't really need to send a response, so we don't take the caller's PID. Instead, we simply do the action and move on. To test it out, we can send a few messages. Note that when we want to get something, we have to receive the response ourselves. This works, but it's kind of obtuse. Since we defined this messaging protocol, it would be nice if we provided some helper functions that did the messaging work for us, so callers don't have to think about the exact format. Our put function is pretty basic, as it just sends the message and returns. Our get function is a bit more sophisticated, as it actually awaits the response and then returns that. Remember that these are just ordinary functions that the sending process can choose to invoke. These are not special, and they certainly don't cross process boundaries. There are some minor improvements we could make here. Our response from get should probably include some metadata about the map, so that the caller doesn't accidentally receive the wrong message from another process and think it's the map response. And this whole thing could be overhauled to use GenServer instead. But this serves as a pretty basic illustration of Elixir's processing capabilities fairly well. Although the language's data types are purely functional and hence immutable, we can still have a changing mutable program in the form of actors. Alright, now that we've done a deeper dive into Elixir's concurrency primitives, let's switch gears back to our Project Euler problem. As a reminder, here's our Scala program. We read in the file, sorted the list, calculated the alphabetical value of each element, and then summed the result. Our Elixir program is going to look a lot like this. First, we import enum. This isn't strictly necessary, but importing its names into scope means we can write map and reduce, rather than qualifying them as enum.map and enum.reduce every time. Now read in the file. Reading in a file returns a 2-tuple indicating what happened. The happy path, where everything went well, returns the atom OK, followed by the file's contents as a string. If something goes wrong, it returns the atom error followed by an error code. I don't really care about the error case here, so we'll just bail out in that situation. If we read the file successfully, we get rid of the quotation marks, split at commas, and sort the result. Note that the sort function comes from the enum module we imported before. Next, we compute the value for each word. Elixir's version of Scala's zipWithIndex is called enum.withIndex, and it accepts an optional argument indicating the value to start counting at. Since the Project Euler problem treats the first element as being at position 1, not 0, we'll just start counting there. We map over this indexed list, pattern matching to separate the index and the word. Inside the mapping function, we convert the string into a list of character codes, get each character code's position in the alphabet as an integer value, and sum the result. Enum.reduce is Elixir's general-purpose fold operation, but we could have also used enum.sum here as we did before. Once we have the alphabetical value, we multiply it by the index. Finally, we sum the result and print it out. And this solves Project Euler problem number 22 in Elixir. We'll definitely be revisiting the beam and discussing more concurrency techniques in future videos. But for now, be sure to tune in next time when we take a look at problem number 23 in Go, Google's flagship high-level programming language.